Okay. Determine the moment of inertia of the shaded area with respect to the centroidal axis. So first, let us try to determine the centroid of this area. So I'm going to consider this is the first area. This is your first area. So this is equal to 48 mm. And the thickness is 8 mm. So this one is now your 8 millimeter. So we have, this is the given x-axis. And this one is the y-axis. So we have your y-axis. So let us try to consider your area 1 in here is equal to, we have 8 multiply this one by 48, and this is equal to 384 square millimeter. So we have your x1 in here. So the y-axis in here lies within the centroid of this area. So your x1 in there is equal to 0. So your y1 referred from the given x-axis. So this one is the centroid of this area. This is the centroid of this area. Therefore, this is now your y1. So consider this is your y1. So the value of y1 is now equal to, so this is equal to 48 is 24 up to this point. And then we have the thickness of this, and that one is equal to 6 inches. So your y1 therefore is equal to 24. This is 24, and this one in here is 6 millimeter. Hence, the value of y1 is equal to 24 plus y1 is 24 plus 6. So that one is equal to 6 millimeter. So 24 plus 6, and that one, this is equal to 30 millimeter. So we have 30 millimeter. Now let us proceed to the second area. So I'm going to consider this one in here as the second area. So for area 2, so we have 24, so this is 48 millimeter. This one in here is 6 millimeter. So again, we have the x-axis. So this is the x-axis. And at the center, of course, now the y-axis. So this is the y-axis. This is 24, and that one is 24. So we have your area 2 is equal to 48, multiply this one by 6, and this is equal to 288. So this is 288 square millimeter. Your x2 in here is 0 because your y-axis lies within the centroid of the area. So we have your y sub 2 is now equal to, this is your y sub 2 from the centroid of the area. This is equal to, and then the distance is. So we have your y sub 2 from the x-axis. So y sub 2 is now equal to, now of course from the centroid, this one is equal to 3 millimeter, and this one up to this point is equal to 48, and that one is 6. So 48 plus 6, this area. So let's write to this area. So we have now your area 2. This is now your area 2. So this is 24 millimeter. Area 2, that is 24 millimeter. So the area in here is equal to, so this is equal to 24 by, so this is 24, multiply this one by 6, and this is equal to 144. So we have 144. So that one is equal to 144. So we have a total distance in here is equal to 48 plus 6 is equal to 60. So up to this point and up to this is equal to 60 millimeter. Hence, 60 minus 3, so your y2 is equal to 57 millimeter. So that is 60 minus 3. Now, let's proceed now to our area 3, which is, this is now your area 3. So for area 3, so this is your area 3. So that one is equal to 48 millimeter. This is 6 millimeter. So the x-axis is, this is therefore the x-axis. And from here is now your y-axis. Again, so that is your y-axis. So this is 24 and that one is 24. So that your area 3 is now equal to 48 by 6. 48, multiply this one by 6, or this is equal to 288. 288 square millimeter. So your x3 again is equal to 0 because the y-axis is within the centroid of the area. So your y3 is now equal to, so this is therefore your y3 from the centroid. So this is your y3. And that one is 6 over 2, or that is equal to 3 millimeter. So let us try to determine now the centroid of the area. So the centroid of the area, so I'm just going to tabulate it in here. So we have the centroid of the area. And then we have now the summation. So we have your area 1, we have your area 2, that is your area 3, and we now have the summation. So now the corresponding area for area 1 is 380 84 square millimeter. For area 2, it is 144. And for area 3, that is 288. So this summation of this is equal to 816 square millimeter. So we have your x, so 0, 0, and 0. And then we now have your y. So your y, 1 is 30 mm, y2 is 57 mm, and y3 is 3 millimeter. And then we now have your AIX. So this is your A times X, that is, and then we now have your A by Y. So this is your A times Y. So 389 by 30, 11, 5, 20. So 11, 5, 20. 144 by 57, so that is 8208. That is 8208. And 288 by 3, we have 864. So that is 864. So the summation is now equal to 2592. That is 2592. Now, so that your bar x in here is equal to 0, and your bar y is now equal to summation AY all over the total area. And this is equal to 20592 divided by the total area, and that is 816. So your bar y is now equal to, bar y is equal to 25.235. 25.235 millimeter. Now, knowing now the location of the centroid, we are now ready to determine the centroidal moment of inertia. So the moment of inertia with respect to the centroidal axis. Okay, so from this figure, bar x is equal to 0. Then the location of YO is the same as that of Y. And then the location of XO is 25.235 mm from the x-axis. So from the x-axis, so it is somewhere else, 25. Okay, so somewhere else at this point is now your x of O. This is your x of O, and your bar y is equal to, so this is now your bar y. That is the location of the centroid. So your bar y is equal to 25, that is 25.235 millimeter. It's 25.235 millimeter. Now, let's try to get now your first area. So the first area, this is the first area again. So we have your area 1. So this is the x-axis. And then we now have the y-axis. We have your y-axis, and then, this is the x-axis. So at this point is the x-axis. So this is your x-axis. So we now have your y-axis. So we have at this point in here, this one is equal to. So this is okay. So we have 6 millimeter, and this is equal to 48 millimeter. Now, the centroid of this area is located at this point. So, this area alone. And this one in here is equal to 24 millimeter. So, this is equal to 24 millimeter. So, we have 24 millimeter. And then we now have 24 millimeter. Now, such that this distance in here up to your x, this is equal to 30 mm. So, this is equal to 30 millimeter. So, the centroid of the area is located 25.235 millimeter from the given x-axis. So, that is your C. That's C in there. And this is equal to 25. So, this one is equal to 25. So, we have 25.235 millimeter. Now, such that this distance in here from the centroid of this area to the centroid of the composite figure, we call this one as your dy1. So your dy1 is now equal to 25. So we have now, so this is 24, that is 30 minus 25.235, or dy prime, dy1 is equal to 4.765 mm, 4.765 millimeter. So that is 30 minus 25.235. So this is the distance. Your D in here is the distance from the centroid of the composite area to the centroid of this area. Now, let us try to determine now the moment of inertia with respect to. So, this is now your x sub O. The moment of inertia with respect to x sub O and y sub O. So, the moment of inertia with respect to x sub O is now equal to, at this time, we will be using the parallel axis theorem, or the transfer formula for moment of inertia. So we have a rectangular area. So this is the moment of inertia at the centroid of this rectangular area is equal to bh cubed all over 12. Since we have to transfer that to the centroid of the composite figure plus a dy1 square. So your IXO1 is now equal to B is 8 millimeter. So this one in here is 8 millimeter. So we have 8 by, we have 48 cube all over 12 plus your area 1 is equal to 384. So that is 384. Multiply this one by dy1 is 4.765 square. So that your IXO1 is now equal to 82,446. 82,446.806 millimeter to the fourth. And we now have your IY01 since it lies within the centroid of the area. So your bar x is equal to 0. And this is therefore equal to BH cubed all over 12. At this time again, your base in here is now the dimension parallel to the y-axis, and that is 48. So we have 48. So this is 48 by 8 cubed all over 12. So 48 by 8 cubed all over 12 is equal to 48. So that is equal to 48 point. Okay, so I'm going to use this blue. Okay, so we have 2048. That is 2048 millimeter raised to the fourth. Now, let us proceed now to the second area. And that one is now the second area. Okay, so we have the second area. So 12, 12, so we have, this is the y-axis, y sub O. This is the x. This is your x. This is your y at the same time, your y sub O. And we have your x of O. So this is now your x of O. This is your x of O. And the distance from the x-axis is equal to 25. So this one in here is equal to 25.235 millimeter. So the distance from the centroid of this area, so this is the centroid, to x of O, this is your x of O, is equal to, so this is now your dy2. So we now have your dy2. So your dy2 is equal to, so this is equal to, so from this up to this one is 60. So we have 60 millimeter. 60 minus 25.235 minus 3. Okay, so that is minus 3 because this one in here is 3. So 60 minus 3 minus 25. So this distance in there is equal to, so that one is 3 millimeters. So 60 minus 3 minus 25.235 is now your dy2. So the value of dy2 is now equal to 31.765. 31.765 millimeter. So we're now ready to determine now the moment of inertia with respect to x of O. So the moment so the moment of inertia with respect to x of O2, again, the centroidal moment of inertia of this area, and that one is now your b h cubed all over 12. Plus, because we have to transfer this moment of inertia to x of o, a dy sub 2 square. And this is equal to, our b in here is equal to, so this is 12, so we have 24, and the thickness in here is 6 inches, 6 millimeter. So your b is 24, h is 6 cubed all over 12, plus area is equal to 144, multiply this one by dy to square, that is 31.765 square. And this is equal to, so this is equal to, this is therefore equal to 145,730, 145,730.192. 192, we have millimeter raised to the fourth. Now, let us try to determine now your IY, since again, it lies within the centroid. So this is bh cubed all over 12. So again, your b in here is equal to 6. Your h is equal to 24 cubed all over 12. So that your IY2 is now equal to 6912 millimeter raised to the fourth. Let us now proceed to the next area. So we now have the last area, which is this area. So this is therefore the area. We have 6 millimeter, and this one is 48 millimeter. So we have the y sub o is somewhere else at this point. That is your, so this is the third area. So this is your y sub o. This is the x-axis. So this is now your x-axis, and this one in here is now your x of o. So this is your x of o, and the distance from the given x-axis is 25 points. So this is of course the centroid. So this is now your 25.235. That is 25.235 millimeter. So we have 25.235 millimeter. So from the centroid of this area, so this is now the centroid of this area to the centroid of the composite figure. This is now your dy3. So we have dy3. And dy3 is 25.235 minus 3 millimeter. And that one is equal to 22.235. So this is 22.235 millimeters. So it's 25.235 minus 3 inches. So let us try to determine now the moment of inertia with respect to x of O. So the moment of inertia with respect to x of O is again the centroidal moment of inertia of that area, b h cubed all over 12 plus a, we now have your dy3 square. So your ixo3 is now equal to, so your b in here is 48 by 6 cubed all over 12 plus the area is 288. 288, multiply this one by 22.235 square. So your ixo3 is now equal to, this is equal to 143. So we have 143, 249. So that is 249.825 millimeter raised to the fourth. And your IYO3 is again BH cubed all over 12. It is again within the centroid of this rectangular area. So this is your B again, is now your 6. This is your B. Multiply this by 48 cubed all over 12. And this one is now equal to 8 cubed over 55,296. This is 55,296 millimeter raised to the fourth. Now, so that the moment of inertia about the centroid is equal to ixo1 plus ixo2 plus ixo3. And this is therefore equal to 37,1426. Because that is 0.823, that is millimeter raised to the fourth. And your IYO is equal to IYO1 plus IYO2 plus IYO3. And this is equal to 256 millimeter raised to the fourth. So we now have the moment of inertia about the centroid of this composite figure in the XO axis and in the YO axis. Determine the polar moment of inertia of the area shown with respect to O. So this is your point O, and the polar moment of inertia with respect to the centroid of the area. So again, let us try to divide this into three areas. So we have your quarter of a circle is now the first area. So this is the first area, and then we have the second area, and this is now the third area. So let's start now with the first area. So this is now the first area. This is 4. So I need 4. Again, so we have the first area. So this is your first area. So we have, this is the x-axis. And this one is the y-axis. So this is your x, and that one is now the y-axis. This 100, that is 100, so the radius of this area is equal to 100 millimeter. Now, the moment of inertia about the x-axis for area 1 is equal to pi r to the fourth all over 16. So you can see this one in the table of moment of inertia of common geometric shapes or geometric figures. Okay, you try to look at the orientation of the axis. So this is equal to pi. Multiply this by the radius, and the radius is 100 raised to the fourth all over 16. And this is therefore equal to 19.635 times 10 to the 6 millimeter raised to the fourth. Similarly, the moment of inertia with respect to the y-axis is still pi r to the fourth all over 16. That is pi, we have 100 raised to the fourth all over 16. So we have 19 millimeter raised to the fourth. Let us now proceed to the second area. So this is now the second area. So we have your area 2. So this is 50 mm. And this one is 100 mm. Now, so this is the y-axis, and this one is the x-axis. X, and this is your y-axis. So this is the area. So that the moment of inertia about the x-axis for area 2 is now equal to, since the base of this rectangular area coincides with the x-axis, so we can make use of the moment of inertia about the base of this, and that is bh cubed all over 3. And your b in here is equal to 50, and your h is equal to 100 cubed all over 3. And this one is equal to 16.667. 16.667 times 10 to the 6 millimeter raised to the fourth. And then your IY2 is now equal to, again, this side in here coincides with the y-axis, so we can make use of the moment of inertia about the base of a rectangular area. And that is bh cubed all over 3. So this time your b is equal to 100, and then your h is 50 cubed all over 3. So your IY2 in here is equal to 4.167. 167 times 10 to the 6 millimeter raised to the 4th. Let's now proceed to the last area. So for the last area, which is this one in here. Okay, so this is now the last area. So this is the last area. So we have 100 millimeter, and this one is 50 millimeter. Now, again, this is the x-axis. And this one is the y-axis. So this is your x, and this one is your y-axis. Now, again, the moment of inertia about the x-axis of this area is again bh cubed all over 12, because the base of this rectangular area coincides with the x-axis. So this is bh cubed all over 3. And this is equal to 100. We have 50 cubed all over 3. And that one is equal to 4.167 times 10 to the 6 millimeter raised to the 4th. And your IY3 is still, it coincides. The base in here coincides with the y-axis. Again, that is bh cubed all over 3. So this is your b is 50. Your h is 100 cubed all over 3. So this is 16.667 times 10 to the 6 millimeter raised to the 4th. Now, so that your Ix is now equal to Ix1, 19.635 times 10 to the 6 plus 16.667 times 10 to the 6 plus 4.167 times 10 to the 6. And this is equal to 40.469. 469 times 10 to the 6 millimeter raised to the 4th. And your IY is equal to IY1, 19.365 times 10 to the 6 plus IY2, 4.167 times 10 to the 6 plus IY3, 16.667 times 10 to the 6, and that is equal to 40.469 times 10 to the 6 millimeter raised to the 4th. Hence, the polar moment of inertia about point O is, with respect to O, this now point O, is now equal to Ix plus Iy. So the moment of inertia is Ix 40.469 plus Iy 40.469, or that is equal to 80.938 times 10 to the 6 millimeter to the 4th. Since we are also required to determine the polar moment of inertia of the shaded area with respect to the centroid, so first let us try to determine your bar X and bar Y, or the centroid. Let's consider the first area again. So this one is now the first area. Okay, so the radius is equal to 100 millimeter. So this is your O. So that is the radius is 100 mm. Now, so this is the x-axis. So this one in here is the x-axis. And that is now the y-axis. So we have your y-axis. Now, so that your area 1 is equal to pi r square all over 4. So this quarter of a circle, that is pi, we have 100 square all over 4. And this is equal to 7853.9186 square millimeter. So let's try to determine your x1 and x sub 2. So your x1, considering now that this is the centroid of this area, hence this is now your x sub 1. So we have your x1 and this is now your y1. So we have your y1. So your x sub 1 now your x sub 1 is now equal to 4r all over 3 pi from the table of your centroids. So this is 4r is equal to 100 all over 3 pi. And this is equal to negative 48.4413. So that is minus 4r over 3 pi because this area 1 is your x is to the left of the origin. So we have negative 48.4413. And your y1 is still 4r over 3 pi. So that is positive above the origin 4r all over 3 pi. That is equal to 48.4413 millimeter. Let us now proceed to your area 2. So with this is now your area 2. Okay, so we have your area 2. So this is 50 mm. And this one is 100 mm. So that is your O. So again, this one in here is the x-axis. And this one is the y-axis. Now, so that your area 2 is now equal to 50 multiply this one by 100, or that is equal to 5,000 square millimeter. And let us try to determine x2 and xy2. So it's the centroid of this area. Now such that this is now your x sub 2. And this one is now your y2. So that your x sub 2 is equal to 50 over 2. Okay, so that is 50 all over 2 or 25 millimeter. And your y sub 2 is 100 all over 2 or that one is 50 millimeter. Now, the last area. We now have the last area, which is now your area 3. This is 100 millimeter and this is 50 millimeter. So this is your y-axis and this one is your dito ang x-axis. So we have the x-axis and we have the y-axis. Now, so that your area 3 is equal to 100 by 50, that is 5,000 square millimeter. Let's try to determine now your x sub 3. So this is the centroid of this area. So we have your x sub 3. This is your x sub 3. And then this one in here is now your y sub 3. Y sub 3. Now, your x sub 3 is 100 over 2, or that is equal to 50 mm, and your y sub 3 is equal to 50 all over 2, and that one is 25 millimeter. So let us try to determine now the centroid of this area. Okay, so let us try to tabulate the results in here. Now, so we have so this is now your area 1, area 2, area 3, and that is your summation. So we have now the area. So for area 1, so we have 7, 8, 5, 3.9186. For area 2, we have 5,000 in square millimeter, and area 3 is 5,000. So the total area is 853.9186. So let's try to determine your x. X1 is negative, so X1 is negative 42.4413, X2 is 25, X3 is negative 50. You try to take note, I was not able to place the negative sign Okay, it should have been negative 50 because it is to the left of the origin. So that is your x3. Now, let's now proceed to y. So your y in here is 42.4413. So 42.4413. And then we have 50 and then negative 25. I was not able to place the negative value in here. You try to take note that it is below the origin. So your y is negative 25. So let's try to determine now your ax. So we now have your a times x. 7853.9186 by negative 42 is negative. Okay, so we have 3, 3, 3. 3, 3, 0, 5155. 5155. 5,000 by 25, we have 125,000. And then 5,000 by minus 50, so we have negative 250,000. So we now have the summation is negative 458, 458, 330. So that is 330.5155. Now, let's try to determine now the value of AY. So again, 7853.9186 by that is now positive 330.5155. 5,000 by 50, so we have 250,000. 5,000 by minus 25, so we have minus 125,000. Okay, so this summation is equal to 458,330.5155. So that your bar x now is summation AX all over the total area. And summation AX is now equal to negative 458,330.5155. Divide this one by 17,853.9186. So your bar x is negative 25.671 millimeter. And your bar y is now equal to summation AY all over A. So we have positive 45,830.5155. So that is all over the total area, 17,853.9186. So we have positive 25.671 millimeter. So the centroid of this area is located at negative 25.671 from the y-axis and positive 25.671 from the x-axis. Now, so let us try to consider now that this is now the centroid of the area. So your bar X is 25. So this one is now the centroid of the area. This is now the centroid. So this is your bar X, and this is now your bar Y. So your bar X is negative 25.671, and bar Y is 25.671. Since we are required to determine now the polar moment of inertia with respect to the centroid. So this is now your D. So let us try to determine the value of D. So your D is now equal to the square root of bar X squared. So the square root of bar X squared, which is 25.671 squared plus 25.671 squared, bar Y squared. So the value of D is equal to 36.304 millimeter. So let's try to determine now the polar moment of inertia. So the polar moment of inertia with respect to the centroid of the figure. So the polar moment of inertia is now equal to the moment of inertia with respect to the centroid plus AD squared. Now your polar moment of inertia, so there's a polar moment of inertia with respect to O. Now at this time, we are required to determine the polar moment of inertia with respect to the centroid. So the polar moment of inertia was computed before, and that is equal to 80.938 times 10 to the 6 millimeter to the 4th. IC plus, we now have the area is 17,853.9186. Multiply this one by D square. And your D is 36.304 square. So that is now your D, 36.304 square. So your IC is now equal to 80.938 times 10 to the 6 minus the product of this, and this is therefore equal to 57.407 times 10 to the 6 millimeter to the 4th. So this is the polar moment of inertia with respect to the centroid of the composite area shown.